Okay, let's get on to the next part that you'll probably find useful when you get onto your third or fourth year courses, or when you're going to take a look at more advanced MATLAB programming stuff. So we're going to take a look at creating cell arrays and logical operators. We're going to review those, and the find command. We're gonna go through those first. So we're going to take a look at cell arrays or cell matrices, and what are these? Well, cell arrays are very powerful because what you can do is each element can store any type of variable that you want. So for example, let's say I wanted to have a cell array that was 4 elements. The first element could be just a single number. The second element could be a structure or another kind of data type. The third element could be a 4x4 matrix. The next number could be a 7x7 matrix, and so on and so forth. So each element by itself is a separate variable altogether. So you can think of a cell array as a variable is an array that stores multiple types of other variables in each index. So cell arrays are pretty powerful because when you're reading in data during multiple experiments, the length or the size of the data might change depending on each experiment that you run. So cell arrays are good for storing matrices of different lengths or different sizes in each index of a cell array. So how you create cell arrays is very simple. You do A equals, and then you use the command called cell, and then you specify 2 parameters separated by a comma. The first parameter is the row, how many rows you want in your cell array, and the second is how many columns you want. So R is for rows and C is for columns. So to create a dynamic cell array, it's just the same thing as you did. Instead of square braces, you use curly braces, and then after you can put in the stuff that you want inside the cell array normally. So to write a cell array or access the contents in a location, you use curly braces. So to copy elements of a cell array, you use round braces. So if you want to actually write a particular, you want to actually store an element inside and the location of a cell array, you use curly braces. If you want to copy cell array elements over, you use round braces. So an example is following. Let's say we have a cell array which is 1 row and 3 columns. And then the first thing that's going to go inside the cell, the first index is the number 3. The second thing that's going to go inside the cell array is a 3x3 matrix full of 1s. That's the 1s command. And the last parameter is a 4x4 matrix full of 0s, and that's going to be stored in the third element of the cell array. So if you do B equals A and then curly brace 2, this is equivalent to accessing the second index of the cell array and grabbing whatever is inside that second slot, which is in this case a 3x3 matrix of 1s. If I wanted to do A and then round brace and then 1:2, what you're doing is you're copying the cell array elements 1 and 2 into a new cell array of C. So this means that the first element is going to be a single number, which is 3, and the second element is going to be a 3x3 matrix full of 1s. If I wanted to access the first element of the cell array, it's the same thing as just accessing the single number, which is 3. And finally, if you want to access the third element, make sure you have curly braces, right? Round braces and curly braces, as we talked about, they're different. Round braces, you're actually accessing you're actually copying the cell array contents, and curly brace means that you're going to get the actual contents inside each slot that you want. In this case, it's a 4x4 matrix. So reviewing logical operators, we're going to go there next. And what logical operators are, think of it as Boolean algebra, as you've seen in 328, or COE 328 or BME 328. It's you're using these to figure out whether certain things are true or false. So these are going to be useful if you want to write a function that will behave differently based on the inputs that you give it. So it's also useful if you want to modify certain elements in a matrix or an array that follows certain criteria. So you have your standard operators here. So when something is less than something, or when something is greater than something, if the expression is true, the output is a 1. If the expression is false, then the output is a 0. Right? So you have, if something is less than something, if it's not true, it's 0. If it's true, it's 1. Less than or equal to is a less than sign with an equals. Same thing with the greater than or equals. Equivalent means that it has to be exactly the same if you want it to be true. And then not equal, in C syntax, it's exclamation mark equals, but here there's the tilde key. The exclamation mark is used as a different context in MATLAB programming, and that is beyond the scope of this tutorial. But the exclamation mark is a reserved keyword that's used for something else. So if you want to do not equal, you have to do squiggly. You have to do a squiggly, a tilde key with the equals, and then you have a logical and logical or, right? So logical and means that both expression 1 and expression 2 have to be true for the output to be true, or means either one of them can be true, and not is just the opposite. So if it was 0, it becomes 1. If it's 1, it becomes 0. Okay, so just a review of logical operators. You've seen this in programming, but just going to give you a little bit of a review here. So we're going to take a look at the find command. So the reason why we want to take a look at logical operators is it's very useful when you're taking a look at the find command. And what the find command does is that it takes a look at a matrix or an array, and then it returns the locations that satisfy a particular logical expression that you supply in the find command. So how you use that is you use the find, and then inside is the expression that you want to evaluate. So, for example, if you wanted to find, so you put a logical operator here with the matrix or the vector that you want to search for, and then what this does is that it returns the locations in the array or the matrix that satisfy this condition. Whatever indices make this expression true, it'll return those locations that make that expression true. So, for example, if I had an array, 1, 3, 6, 2, and 4. If I wanted to find all the locations that made the array, the array greater than 4, it'll return locations 3 and locations 5, because these are both greater than or equal to 4. So this would give you those locations. Right? That tells us that locations 3 and 5, satisfy that logical expression. Here's some more examples. If I wanted to find any locations that were greater than or equal to 2 and less than or equal to 4, what that does then, it'll search through this entire array, looks for anything greater than 2 and less than 4, so we're going to have this one, and this one, so it returns locations 2, 4, and 5. Okay? If I wanted to find anything that was exactly equal to 3, that's the second element. If I wanted to find anything that's not equal to 2, it returns everything except for the third element, except for the third location, right? 2, not equal to 2. So if not equal to 2 is here, this means it will return everything except for the fourth location, and that's all we get. So using these indices, right, we can modify the arrays based on whether certain criteria is met. So for example, if I wanted to find all the indices, this is a 5-element matrix. This is a 3x2 element matrix. So 1, 2, 3, semicolon 4, 5, 6. This is a 3x2 matrix. If I wanted to find any locations that were greater than 2 and less than 4, it'll be these 3. And then what I can do is I can use these locations and modify them so that they are set equal to 0. So what this means is that for whatever locations are greater than 2, greater than or equal to 2 or less than or equal to 4, I can make these locations be set all to 0. So this is very powerful because you can modify elements where they meet certain criteria that you're looking for. So now this becomes 1, 0, 6, 0, so these locations become 0. Now what this is saying here is find anything that is not greater than or equal to 1 and less than or equal to 3. So pretty much here, so this is your matrix. This is 1, 2, 3 for the first row, 4, 5, 6 for the second row. So anything that is not in between 1 and 3 is essentially the entire second row. And then when you do that, if I want to change it so that I want to change that entire row to be 9, 10, or 11, you can just pretty much do that. Okay. So one more thing before we get on to better things. If I wanted to find any locations in the B matrix which are either 2 or 5, you'll get that, and then what will happen is when you do this, it will change those elements so that they become 10. So anything that's 2 or 5 will become 10. So this was 2, it becomes 10. That's 5, that becomes 10 too. Okay. So let's get on to some more advanced topics. Creating transfer functions, impulse response. This is more for signal analysis stuff. And then we can get on to some more cool topics here. So creating transfer functions. So we have seen transfer functions in a variety of different courses. Differential equations, control systems, other mathematics courses, Math 312, signals and systems, anything dealing with signal analysis. We've seen transfer functions in some way, shape, or form. So transfer functions are dealt in the Laplace domain, which is the variable s, And we commonly see two forms of transfer functions in practice. The first one is the one that is more well known, which is called the polynomial format. In this case, you have powers. This is the polynomial equation. You have powers in decreasing order. For example, I could have 2s plus 1 here, and then s squared plus 3s plus 4 at the bottom. Right. So you have a polynomial format means that you have powers of s in decreasing format, and then each number, each power of s to the power n, s to the power n minus 1, has a coefficient that is multiplied with it. And then next we have something which is called the zero pole gain format. And what that does is that we can assume that because this is a polynomial equation, we can factor this into n different roots. So we can do that for the top and we can do that for the bottom. And we can decompose it so that it looks like this. So the roots at the top are known as zeros, and the roots at the bottom are known as poles. And there could be a case where you have a multiplicative gain in front of it, which we'll call k, which is gain, so zero pole gain format. So to create the first style of transfer function, you basically use the tf command. And what the tf command does is that it creates a transfer function object that will be in polynomial form for you. So how this works is that you supply two arrays of coefficients. The first array is the numerator, which is the numerator part of the equation, and you specify the coefficients in descending order from the highest power down to the lowest power. And then you do the same thing for the denominator, where you specify the highest power of the denominator. Oh, sorry, this is a typo. This is denominator, and then down to the lowest power. And then the output will give you a transfer function object that can be used in a variety of different signal analysis functions seen in the MATLAB programming environment. So let's say I wanted to create these transfer functions. Okay? So for example, if I wanted to create this transfer function, the numerator will be 2s plus 1. So this is the highest power, which is 1, so you're going to specify 2 and 1. If I wanted to specify the denominator, so you have 4 coefficients. Okay? And you want to so this is to the power 3, 2, 1, and 0. So you have 1, 2, 3, and 1. Okay? If I wanted to specify just a single number, this is just the order of 0, you specify 5. And if I wanted to do s squared minus 3s plus 2, you specify a minus for the coefficient, because you're technically adding a negative value. That's what you do. So you do 1, minus 3, and then 2. Okay, if I wanted to make this one, you do, so this is s to the power 2, 1, and 0, so you have 10s squared plus 5s minus 3. And then if you take a look here, we don't have a coefficient up to the power of 1. And we assume that's a 0, right? Because it's basically 0 times s to the power 1, so there's nothing. So you get s to the power 4 plus 5s3 minus 4s squared, and then 0s plus 6. Okay, so you get it? So the numbers that go beside each power of s go in decreasing order inside the square bracket. So if you want to specify subtraction, you got to use a negative sign to specify that. So let's code these different transfer function objects. So the first one is 2s plus 1, and then s cubed plus 2s squared plus 3s plus 1. This is 5 divided by s squared minus 3s plus 2. And then this is 10s squared plus 5s minus 3, and then s4 plus 5s cubed minus 4s squared, no s term, and then 6. So how about the zero pole gain format? Pretty much the same thing. This is the case where you specifically know what the poles, zeros, and gain are for that transfer function that you want to take a look at. All right. So if you use the zero pole gain format, it's the following way. So you have ZPK and then bracket, and there are 3 parameters. The first parameter are basically the physical 0 locations. So and then we'll get onto. I'll show you an example. And then these are the pole locations. You specify them as arrays, right? Make sure they're square braces, same like the transfer function object. And then you specify a multiplicative factor of gain, k. So let's say I wanted to create these 3 transfer functions. Okay. So if I wanted to specify a transfer function like this, the gain is 3, and then you have 2 zeros at -2 and then -3. Make sure you specify the opposite of what the sign is, because the zero pole gain format is s minus a number. So if you wanted to get it to be a plus, then it's got to be -2. This is -3. And if you wanted the poles, this is -1, -5, -6. Okay? And then if I wanted to do this one, you'll have a gain of 5, and then I have a 0 at +3, and then I'll have imaginary poles here. So I is supported too. So this is 1 minus I, and then 1 plus I. And then the same thing for this one. I have no gain, it's just a gain of 1. And then you have a 0 at -1, and then 1 and minus 2. So we can specify imaginary poles and zeros too, and you have to take note of the factors, with addition. Let me see. What does it say? Right. Of course, and what this is saying is that you have to be sure that whatever you see, the sign is the opposite. So when you have a plus 2 here, this is a minus 2. You have a plus 3, this is a minus 3, so on and so forth. Okay. So let's call these. Okay. Actually, one more thing. If you wanted to specify multiple poles, let's say you have s plus 2 and then you have to the power 3. So you're going to do minus 2, minus 2, minus 2. So you have to specify as many poles as you have repeated. All right? So let's call these transfer function objects. Let's say we have zpk, and then you have bracket, and then inside the brace we have s plus 2, s plus 3, and then on the bottom s plus 1, s plus 5, s plus 6. Okay, so that's these are the locations of the zeros, the poles, and then the gain. And then the same thing here. You have 3 for the 0, s minus 3, and then you have the 2 imaginary poles with 5, and then you do the same thing here. Okay, you have let me see here. You have s plus 1, and then s minus 1, and then s plus 2. Yes. All right. Sorry, it's s plus 1. Sorry, you have a gain of 1. So there might be a case where you have some poles or zeros that are deemed insignificant. In 639 terms, what that means is that when you plot your poles and zeros on the real and imaginary axis, there might be cases where some poles and zeros are very close to each other. That means they'll just cancel each other out from the top and the bottom of the equation. And there might be poles or zeros that are very, very far away from the imaginary axis, and their contribution, both of those, is pretty meaningless. So to get the best transfer function, you should remove those non-significant poles, or insignificant poles, or zeros. And the best way to do that is to use the min-real command. And what the min-real command does, it performs a minimum realization of your transfer function, and that removes pretty much any poles or zeros that are insignificant in your transfer function. So you use the min-real command. The input that goes in is the transfer function object that you created either by using TF or ZPK, and you get an output which is the minimum realized transfer function of the input that you specified. So transfer functions are very useful because they model the input and output relationship of a system. So once you know what the transfer function is, all you got to do is just specify any input into the system, or where you have a system that's defined by some transfer function, and the output that you get is you can use that transfer function to get any output based on the input in that transfer function. Okay, so the two most common inputs that we use to assess the reliability and stability of systems is using what are known as the step and impulse inputs. So the first case, which is the step input, it's defined as anything that's less than 0 is 0, and anything greater than or equal to 0 is set to 1. So you can think of it as like a box kind of graph. But 1 continues forever up to infinity. And then with an impulse input, in terms of MATLAB, it's defined as anything except the time is equal to 0 is 0, and right when it's equal to 0 is 1. So this is in MATLAB terms, where in terms of MATLAB and getting it to efficiently calculate stuff. In the MATLAB environment, we're going to assume that it's 1. That's what it does. So you can find the step and impulse response, which is basically the response of a system defined by its transfer function due to a step or impulse input. So step response means it's the response due to a step input. Impulse response means that it's the response due to an impulse input. And then you have, let me see here, the output, when you run the step or impulse response commands, will give you a set of x and y arrays. The x array gives you the set of time values, and the y array tells you what the amplitude is at each corresponding time point in the x-axis, in the x array. So something to note. Okay, notice that we're specifying the transfer function we are specifying in the S domain, yet the output is in time domain. This is perfectly normal because the Laplace transform is used as a tool to get the time domain response more efficiently. Time is essentially what we want, but we're transforming it to a different domain to analyze the characteristics a lot easier. That's why it's called a transform, Laplace transform. Okay, so to calculate the impulse response, you use the impulse command, and you do that by doing impulse, and then you specify a pair of round braces, and what goes inside is the transfer function object that you specified using either TF or ZPK. Okay, you can also when you run this command, what this does is that it creates a new window that plots the impulse response over time for you. It automatically figures out the ending time, so if you want to specify the manually specify what the ending time is, you can use impulse, and then you specify another parameter, which is the final time. It's just a number, and then it'll tell MATLAB where you want to end the simulation time at. Also, it pretty much follows the same style as this. It creates a new window, but it just changes it so that you are simulating it up to a end time that you specify. You can also analyze the impulse response at particular points in time. So if you have a set of time values that you want to evaluate the impulse response at, you can specify this by doing a array of values, where each point in the array denotes which time you want to evaluate the impulse response at, and this creates a new window for you that reflects the same thing. You can also repeat the same style of how you can call this function by the following. You pretty much repeat the same three things, but you just append an output. So what this will do is that it will generate a set of amplitude points, which is your y, and then the time points, where each time index, or the actual time that this particular amplitude happens at. In this way, it doesn't generate a plot. What it does is that it will output two different arrays. So the impulse response values and then the time points at each of the values. So this way, if you wanted to graph more than one impulse response graph on a single window, then you can use these tools to be able to do that. So you can use plot or subplot to do that kind of thing. So to calculate the step response, you use the step command. Just like how you use the impulse command, the style of invocation, how you call the step command is very similar to how you call the impulse command. Just replace all the impulses with steps, and you're done. So this pretty much will produce everything just like the impulse response would, but you're doing it for steps. I'm not going to go through that. It's just you're just replacing all the impulse with step. So for example, let's try finding the impulse and step response with two different transfer functions. So for example, if I wanted to create this transfer function 5 divided by s squared plus 3s plus 2, I'll do a TF, so you have 5, and then you have 1, 3, and 2, right? So s squared plus 3s plus 2. And then if you wanted to create this transfer function, you have 3 at the top, and then you have s squared. There's no s term, which is 0 times s, and then 25. So what I'm going to do is I'm going to create a window that will graph the step response up to 7 seconds. Okay, I'm going to label, once that's done, it'll produce a new window, and I'm going to label the time axis, and I'm going to label the x-axis, which is time, and I'm going to give it a title, which I'm going to call it step. And then I'm going to create a new figure, and in this figure, I'm going to plot the impulse response for this. So what I'm doing is, this is the step response for the first transfer function, this is the impulse response for the second transfer function. And then I'm going to, once the window is created, I'm going to label it with, I'm going to label the x-axis as time, and then I will give it a title, which is called impulse. And it looks like that. Okay, so notice that the end time is 7 seconds, the end time here is 4 seconds, and this is what the impulse and step response would look like. So let's try something a little bit more advanced. Let's say I want to plot both of these graphs on a single plot. So what you do is I'm going to run the step command, and then for the first transfer function, I'm going to specify exactly which time points I want the step response to be evaluated at. So I'm going to go from 0 to 7 in steps of 0.1. And similarly, what I'm going to do is I'm going to do the same thing for the impulse response. For the second transfer function, I'm going to go for the same thing, 0 to 7 in steps of 0.1. And then what I'm going to do is I'm going to plot both of these on the same graph. So you have these correspond to your step input, right? I'm going to make it a red graph. I'm going to draw, I'm going to connect all the points, and then I'm going to do the same thing for the impulse response. And then what I'm going to do is I'm going to make it green, and then I'm going to draw a line through it and have x's at each point. I'm going to label the x-axis, which is time, and then the title, I'm going to call it step and impulse responses, and then I'm also going to give it a legend. So the first set of points corresponds to the first transfer function, and the second pair of points corresponds to the second transfer function, which is this. And it's going to look like this. Okay, that's not too bad. So you're just plotting the both step and impulse responses together on the same graph. So MATLAB is a great numerical analysis tool. So we covered transfer functions. Now we're going to go through finding roots of equations of polynomial form and nonlinear equations. So sometimes we encounter polynomial equations that are of third order or higher. So most conventional calculators that exist today can only find roots up to the third order. So you can only find up to 3 roots. Anything bigger, it won't be able to handle it unless you have a Texas Instruments or any calculator that is able to find this stuff. But most scientific calculators that range between $15 and $30, they're not able to find roots of a higher than third order. So the good thing about MATLAB is that you're able to find roots of any order for any equation that you want. So the sky's the limit for MATLAB in this case if you want to find the roots of a polynomial equation. So we're going to look at finding roots for 2 very popular forms of equations. The first one, as I talked about, is your standard polynomial form. an times x to the n plus an1 times x to the minus 1, so on and so forth. This is your standard polynomial equation. So for example, a polynomial equation would be 3x cubed plus 6x squared minus 9x plus 4, for example. Alright, so the highest power was, in this case, in that equation, it was to the power 4. That means you're going to have 4 roots. So whatever the highest power is, fundamental theorem of algebra tells you that the highest order of your system or the equation will tell you how many roots you've got. So the next form is not polynomial equations, but they're nonlinear equations. Equations such as, sine x plus 3x times 4 or something, or a to the power of x minus 2, or some equations that do not fall in the polynomial form. Okay, so you're going to have, unfortunately, they don't factor very nicely using the using in the polynomial form. So you're going to have to use more non-conventional methods like Newton's method or bisection method or any other root finding tool that you're used to find roots. But we'll get to that in a little bit. So to find roots using the first form, you're going to use the roots command. All right, and how the roots command work is that you specify an array of coefficients where the coefficients are in descending order. So pretty much like how you saw for the TF command, you're going to do it in the same style here. And the output is an array of the same size that you specify. It's an n by 1 array where n is the total number of roots. So here are some examples. If I wanted to find the roots of p1x, which is 3x to the power 4 plus 2.5x to the power 3 plus x squared minus x plus 3, if I wanted to find the roots of those, or the next equation, which is 5x to the power 5 plus 3x to the power 3 minus 2x squared minus 1, notice that the first equation is of order 4, which means we have 4 roots. So if I wanted to find the roots of this equation, you do roots, and then you do bracket, right? You have the 2 brackets here, right? And then you specify a pair of square braces, and then you'll have 3x for 2.5, right? So 3, 2.5, 1, minus 1, and then 3. When you run that, you will get the following output. So this is the first root, this is the second root, third root, and fourth root. So this is telling us that they're all imaginary roots. All right. If I wanted to find the roots for the second equation, it's very simple, right? So for this one, you have 5x5, right? There's no coefficient for 4, so 0, 3x3, then minus 2x squared, right? You have no coefficient for the x, and then minus 1. When you do that, you get 5 roots. So this is the first one, and then the rest of them are imaginary. So for nonlinear equations, for example, the sine x or the cos x or whatever, you have to use f0. f0 means find a 0 or find a root. This finds the root of a nonlinear equation based on an initial guess. So for non-conventional methods for finding roots, like Newton's method or bisection method, you always have to start off with an initial guess. And what f0 will do is that based on your initial guess, it will find the closest root that's based on your initial guess, and it will approximate that root for you. Okay, so how f0 works is that it uses a variety of different root finding methods like Newton's method or bisection method. It depends on the type of equation that you use, and then it'll use the best one that matches that particular problem. Okay, so how you use the function is very easy. You use the f0 command, and then there are 2 parameters that go in. The first parameter is a function handler of a single variable. So because f0 only works for finding roots of a one-dimensional nature, so it only relies on 1D. Okay, or it only relies on 2D, not a 3D graph. So you create a function handler like you would normally, and then you specify an initial guess in the second parameter. So you just specify what you think the initial guess. Just specify an initial guess what you think the root is close to. Okay, so the thing with nonlinear equations is that if your nonlinear equation is more than 1 root, you have to run f0 as many times as there are roots. Because what will happen is that when you run f0 the first time, right? And it's going to move towards what the closest root is, and then that only tells you what one of the roots are. If you want to find what the rest of the roots are, you have to choose an initial guess that is far away from the first guess that you made, or it's going to just tell you what it's going to do is that it will just give you what the first root was, which you've already found. So you have to be sure that you specify an initial guess that is a little farther away from the first initial guess. You're able to get that root. So let's try finding some roots for sine x. Okay, so let's create a function handler of sine. You have the @ sign, and then inside you have the variable x, and then you have sine x. Okay, and then what I'm going to do is I'm going to run this 3 different times. The first time I have an initial guess of 0.5, and when you run that, what will happen is you'll get this root. So this is actually minus 1.8 times 10 to the power of minus 28. So it's almost 0 because you're approximating the root. And then what you're doing here is you're going to run it one more time with an initial guess of 2.5, and this gives you 3.1416, which is basically pi. So when you start, because sine is in radians, where if you were to start at 2.5, this is very close to pi, so it just moves to pi. And if I were to specify minus 4, it's going to be minus pi. So the root that they give you is based on your initial guess. It's always heavily based on that initial guess. So here's another useful function if you want to evaluate polynomial equations at a point or several points. So this is very useful if you want to see how it works when you want to get into regression or finding the best line of fit between for a set of points. How much? Oh, okay, good. I got maybe half an hour more. Okay, so given a polynomial equation where its coefficients are stored in an array, so if you remember, the style of the way the coefficients are stored are very much like what you've seen in the TF or the ZPK format, right? Sorry, just the TF, not the ZPK. But you store the coefficients in a descending order into an array called coefs, and then you specify the points that you want to evaluate the polynomial at in this second parameter, and then it gives you the evaluated points at each corresponding. So, for example, this x could be a single vector, a single value. It could be an array. It could be a matrix. And what this will do is that for each number that's in your vector or matrix, it'll evaluate the polynomial equation at that particular number in that corresponding location. And then the output will basically will give you what the evaluated points are for each of those corresponding locations for the output. So let's evaluate. So for example, let's evaluate 3x squared plus 5x plus 7. So you're going to have 3, 5, and then 7. So you're writing out the coefficients in descending order. So if I were to have let's say a 4x cubed, and this doesn't exist, you'd have 4, 0, and then 5 and 7. Okay? And then these are the points that I want to evaluate at. So I want to evaluate this equation when x is equal to 5, 7, and 9. So when I run through this equation, what I'm going to get is the first element is basically you're going to substitute 5 into here, which you get 107. The next element, you substitute 7, you get 189. And the next, you substitute 9, you get 295. If I were to do the same thing by creating a 2 by 2 matrix, what this will do is that it'll take each number, evaluate the polynomial, and then place it in its corresponding position for the output. So for example, in the top left corner, when you put in 1, you get the top left corner is 15. And then when you substitute 2, you get 29. And then 3 is 49, and so on and so forth. Okay? So, if you have two polynomial equations with their coefficients stored in separate arrays, so this is in the same style as the TF function that you wrote. If you have coefficients that are stored in different arrays, and you want to multiply two polynomial equations together, you can use what's called the convolution command. I'm not going to be going through convolution in the context of signals and systems, but I'm going to be going through it in terms of multiplying polynomials together. So when you use the conv command, you specify two arrays. So there are arrays of coefficients in the same style as TF, and then when you use the convolution command, y will give you what the coefficients of what would happen when you multiply the two polynomials together. And this is what it would look like as an example. So here's an example. Let's say I have a polynomial equation x cubed plus 2x plus 4. Okay? And then I have another one which is q 2x squared minus 1. So when you multiply these physically, right, you'll have x cubed plus 2x squared, which is 2x5, and then you have minus 3. So I'm just distributing, and this is the final output that you'd get when you multiply. If you run this in MATLAB, you'll create a matrix, an array of coefficients. So you'll have 1, and then there's no x squared term. You have 2 and 4. And then you have 2x squared. There's no x term. You have -1. And then when you do convolution of p and q, this is what you'd get. So you have 2x5. There's no x4 term. You have 3x cubed, 8x squared, -2x, and then -4. So remember, there's no x to the 4 term. So this is pretty accurate. So you can also use MATLAB to perform partial fraction decomposition. So think of this in terms of Math 240, Calculus 2, Vector Calculus, Math 312, or ELE or BME 532, signals and systems when you're trying to do the Laplace transform. You can decompose a equation that consists of polynomial factors in the top and the bottom, if it's a fraction, into a sum of different fractions, multiplied by a particular scale factor. What we mean is the following. If we assume that the equations in terms of s, if we have, let's say, b over a, you're going to have, remember, you can decompose these into poles. You have s, and then s minus p1 minus p2, and so on and so forth. If you were to decompose the polynomial equations into different roots, we can split up each root so that they're represented as a sum of terms. Okay, so when you have n roots in the equation, right, this means that you will have n fractions. Okay, and then what will happen is that if your numerator power is higher than your denominator power, what's going to happen is that you're going to have a residual polynomial here that ensures that this partial fraction decomposition is valid. So we can call partial fractions by using what's called the residue function. All right, the residue actually, partial fractions and residue are actually the same thing. It's just residue is more used in more advanced mathematics courses, and partial fractions is more for introductory basis. So if you want to run if you want to do partial fractions, you run what's called the residue command. So with the residue command, you specify the coefficients, right, in descending order, just like in TF format for B and A. So this is the numerator, that's the denominator, and then what's going to be outputted are 3 different arrays. What P means is that they're the decomposed pole locations. So how you can decompose the fraction into multiple sums of fractions. It'll tell you what the locations are. And then these are the scale factors for each of the fractions. And then K is what happens when your numerator is bigger than your denominator, the order. And then it'll tell you what the polynomial equation is for that. If you have repeated roots, then what's going to happen is that the P and R arrays are going to be arranged like this. So what's going to happen is that when you, for a particular pole, it will give you what the coefficient is for the first order, and then the next coefficient right after it in the array will be for the repeated one for the second order, so on and so forth up to the m repeated roots. So it's going to look like this. So if you have your R array, so these two will correspond, right? So this is for the first repeated root. This is for the second repeated root when you square it up until the mth power. So let's find the partial fraction decomposition of this. So for example, if I wanted to do s minus 4, you'll have 1 minus 4, and then if I wanted to code this, you'll have 1 s squared plus 6x squared plus 11s plus 6. Okay, and then when you run the residue function, this is what you're gonna get. All right, so because the numerator power is less than the denominator, this is empty. So this is telling us that we can decompose this into a sum of 3 fractions. So s plus 3, s plus 2, s plus 1. And then each of them have a scale factor, so this will be minus 3.5 for this location. This is the first element, the corresponding. And then you have 6s plus 2, and then minus 2.5 s plus 1, over s plus 1. So that's an example of how you would do a residue or partial fraction decomposition in MATLAB. Okay, so a couple of things before we get on to more advanced topics. So if you ever wanted to take a small matrix and repeat it horizontally or vertically a finite amount of times, you use what's called the repmat command. Alright, so how this works is you specify the matrix that you want to copy over, and then m and n determine how many times you see the copied matrix horizontally and vertically. So if you were to specify 2, what this will mean is that you're gonna see it repeated 1 time. So m minus 1 and n minus 1 are the amount of times you're going to repeat the matrix vertically and horizontally. So, for example, if I were to make this 2 and 3, you're going to copy this over. You're going to copy this vertically by 1 and then horizontally by 2. So A is the matrix that you want to repeat. So here's a quick example. If I wanted to copy this matrix 1, 2, 3, and 4, 2 by 2. If I want to, this should actually be a 2. That's a typo. I'm sorry about that, but this should be a 2. If you were to do repmat 2, 3, what this is going to do is that you'll see 2 instances on the rows and 3 instances along the columns. So you're going to see 1 instance here, right, and then 3 instances this way. So you're going to get that matrix. So this should actually be a 2, right? So repmat 2, 3, that's what you get. And then last but not least, if you wanted to take a column vector and reshape it so that it would look like a matrix, you can use the reshape command. So x would be a column vector, and then you specify the desired rows that you want and the desired columns. So you're going to reshape a column vector, which is of size m times n, into an m by n matrix. How the reshape command works is that it takes elements column-wise. Okay. So if you wanted to reshape this, so this will create a column vector for us. 1 to 12. It'll be a column vector, and then this is going to tell us that we want to have 4 columns and then 3 rows. Okay. So let me see here. This is you know what? I screwed this up. This should be 3 and 2. Okay, I screwed this up. This should be 3 and 2. So in this case, if you were to do 4 and 3, what will happen is that, you know what? Okay, forget that. This is 2 and 3. That's okay. What'll happen here is this is actually the desired columns we want. This is the desired rows. So I made a little mistake here. So this is the desired columns. This is the desired rows. So if you were to do 4 by 3, what'll happen is that it will make 3 rows and 4 columns, and it'll take the elements in a column-wise. So you'll see that it's distributed this way. So it's going to go. So what will happen is that it just spreads them out this way. So you 1 to 3 and then to 12. If I wanted to do 3 and 4, what this means is that you want 3 columns and 4 rows, and it'll look like that. That's just a little bit of an extra in case you want to reshape a vector into a matrix, but that's okay if you don't want to use it. Okay, so we're gonna start off by we're gonna do some more advanced mathematical analysis. I'm gonna pause the video because I need to drink something because I've been talking for a while. So let me just pause this video. I'm going to take a drink of water, then I'll come back. So, okay, let's get back to this. So, this part of the tutorial is going to cover some more advanced math topics that would be akin to what you'd see later on in the courses that you'll be taking. And you'll be able to see that MATLAB is a really cool tool to use to help you in analyzing a lot of different things. So what we're going to cover first is how to calculate derivatives both analytically and numerically using the symbolic mathematics toolbox. So this is very similar to the Wolfram online math integrator that will give you equations with respect to whatever variable you desire. We can do the same thing with MATLAB. And you'll see that it's a lot easier to see and to interpret and to read. So we can use that. We can also evaluate derivatives at points. We can calculate the definite integral, the area under curves, and so on and so forth. We're going to take a look at how to find the line of best fit with regression. This is, wow, okay. I copied this twice. That's retarded. Guess this is what happens when you are making slides at 3 in the morning. Anyway, so we're going to find the line of best fit. This is more commonly known as polynomial regression or polynomial interpolation. And then we're going to take a look at how to calculate the area under a curve when you only know data points, and you don't know what the actual underlying function is, and you use that by calculating the trapezoidal rule. So you can use MATLAB as a tool for analytically calculating what the integrals and derivatives are. You can see what the closed form equation is with respect to whatever variable you want. In this case, you can do it for x, y, or whatever. And you can also calculate what they are, what the actual numerical values are for when you're using it in MATLAB. So you can do that by using what's called the symbolic math toolbox. And how the symbolic math toolbox works is that you specify what variables you want that will be used to perform your derivatives and your integrals and so on and so forth. So here are the basic steps that you need to do. All you got to do is you got to tell MATLAB what variables you want to use to create the functions that you want, so you can integrate and differentiate. All you got to do is once you tell MATLAB what variables you want, then you just code your equations in C style, just like what you've been doing so far. So you're going to do it almost like a function handler, but not quite. You'll see later what I mean. So once you create these equations, you put them into the functions that differentiate or integrate for you, and you are done. So to do the first step, you have to use something which is called the sims command. And what the sims command does is that it tells MATLAB which variables are going to be deemed as symbolic, so that you can use those to create your equations, to differentiate and integrate or whatever you want. You can also specify more than one variable. All you have to do is just separate each variable with a space. So for example, by using the sims command, you do specify sims, and then you have the variables that you want to specify. In this case, if you want to specify 4 variables, you have x, t, w, and alpha. All right. And then if you wanted to specify just 2 variables as y and x, you do sims y and x. If you just want to specify one variable, which is w, you call it as w. So next, what you do is you code the equations normally. So there's no function handlers this time, and you don't need to do any point-by-point operations because this is a symbolic function. There's no way that you can substitute values into the function. This is just an equation by itself. So for example, if you wanted to create a function which is 5 sine x minus x squared plus 3, as we talked about before, or if you wanted to create a function which was 25 minus x squared minus y squared, you do sims xy, right, x space y, and then you specify the equation using the symbols that you define using the sims command. In this case, you have 5 times sine x minus x hat 2 plus 3. Make sure you don't do any point-by-point operations. You leave the dots out, and you just code it normally. Same thing that you're doing for here, 25 minus x squared minus y squared. Okay. Now that we're finished, let's find the derivative. Okay, so there's multiple ways that you can calculate the derivative. All right, so how you calculate the derivative, the default way is to just specify the equation that you write inside what's known as the diff command. All right, what this will do is that it figures out what the independent variable is by default. In this case, this is x, and then it differentiates with respect to x, and it gives you what the equation is in closed form. If you have a function of multiple variables, right? If you remember from calculus 2, you treat all the variables constant while differentiating just the variable that you want. And in this case, if you have a function of more than one variable, in this case this is g, if you were to do diff g, and then you specify the variable that you want in single quotes, which is x, what this will do is that it differentiates the equation with respect to x while making all the other variables constant, and then you can do the same thing for the variable with respect to y. Okay, so the next form, what this does is that it will differentiate a function n times. So if you wanted to differentiate a function 3 times or 4 times, you specify that number here. It just differentiates the function as many times as you want by specifying the number 2. All right. Also, you can if you have a function of more than one variable, you can specify what you want to differentiate with respect to, and then you can differentiate as many times as you want there. So in this case, if I wanted to differentiate with respect to x 2 or 3 times, you specify that here, and then you leave x there as the variable you want to differentiate with, and then the same thing for y. Okay, so got a phone call. Let me just pause this again. Very sorry, and I'll get back to you. Okay, so here are some examples. Let's say I wanted to differentiate the function f with respect to x, right? So because f is only defined as a single variable x, if you were to do this, the output it'll show you as 5 cos x minus 2x, which is the derivative with respect to x. If I wanted to differentiate the function g, which is 25 minus x squared minus y squared, if I wanted to differentiate that with respect to x, then it will just, the 25 and the y squareds go away, so you're just left with minus 2x. The same thing if you want to differentiate with respect to y. If I wanted to differentiate f twice, you just plug in, f and then 2, and it'll differentiate this twice. So this is basically the derivative of this, which is just minus 5 and then minus 2. Minus 5 sine x minus 2. And then if I wanted to differentiate g with respect to x twice, it'll just give me the number 2, right? Because this is the derivative once, and then if you differentiate it twice, you get minus 2. And then we can repeat the same thing with integration. So I just showed you pretty much how to differentiate. Now this is what we're gonna do this for integration. So you use the int command, int, for integration. All right. Don't confuse it with the type integer. In this case, int is a reserved command here in MATLAB that will find the integral for you. So here are all the possible ways you can run this command. So the first way is finding the integral in closed form. So you're finding the indefinite integral with respect to whatever variable, the single variable here is by default. If I have a function which is more than one variable. If I wanted to find the indefinite integral, what you're going to do is you're going to specify which variable you want to do it to. This is with respect to x. There's no single quotes. And what this will do is that it'll integrate, and then what it will do is it'll leave all the other variables constant while you integrate with respect to x. And make sure, as I said, there's no single quotes. If I wanted to find the definite integral, if I wanted to find the area between a and b on the x-axis or whatever, or if this is a single variable, it'll give you what the area is under the curve bounded between a and b. All right, that's defined by that definite integral. If I have a function that is more than one variable, what you can do is you can specify a definite integral with respect to some variable. In this case, what it'll do is that if I have a function that's more than one variable, I can integrate with respect to y, and then I can provide a definite bounds between a and b. And what this will do is that it will evaluate the function with respect to y, and it'll do your definite integral, but it'll leave all the variables constant. So when you run this function, you're gonna whatever variable is left that you didn't specify, it just treats those as a constant. So here are some good examples using the functions that we defined earlier. If you integrate with respect to f, if you integrate the function f with respect to x, what'll happen is that it'll integrate all the terms, and then you pretty much get that. So our original question was 5 sin x minus x squared plus 3. So then it'll integrate, and that's what you get. And then the same thing if you have a function of more than one variable. If you want to integrate that with respect to x, it leaves the y value, the variable, constant, and then it just integrates with respect to x. And then you can do, oh, there's a typo here. I'm sorry about that. Okay, make sure that there's no single quotes here. All right, so if I wanted to integrate with respect to y, you'll do the same thing. It treats x as a constant. And then if I wanted to find the definite integral for the function f between 0 and 1, this is what it would give you. So 23 over 3 and then 5 times cosine 1. So what this is doing here is that it doesn't know whether or not cosine is radians or degrees, so it just leaves that for you and for you to interpret. And then here, if I wanted to do the function g, remember f and g are defined earlier. We're using those, we're using those function handlers that we defined earlier. If you want to integrate the g, which is a function of x and y, between 0 and 1, just with respect to x, you'll plug this in, and then remember the y is constant. You're just assuming that it's a constant variable, a value rather. Next, what we're going to do is we're going to take a look at the line of best fit. This is known as regression. So what regression does is that you're given a set of data points, and regression will find the best line of fit that minimizes the error between what the coefficients that it determines with the data points. So it minimizes the error between the optimal line that it figures out with the data points themselves. This can be represented in terms of least squares, but I won't go too much into the math. It's too detailed to understand. But I'm just going to show you what MATLAB tools you can use to perform this kind of regression. This is more commonly known as polynomial interpolation. Right? So for this function, we're given a set of x and y points, and now it's our job to figure out the best polynomial equation to fit these sets of points, and it'll draw the best line of fit through all these sets of points. There's different lines you can use. You can use a linear equation, you can use a parabolic equation, you can use a cubic equation, and so on and so forth, and you can specify that order very easily using MATLAB. So, in other words, oh, another phone call. Very sorry. Okay, let's see here. I talked about that. All right, so cool. 18 more slides, not too bad. Hopefully we'll be finished soon. So, in other words, regression. The goal is for a pair of x and y points. Right, or not for a pair of x and y, for a collection of x and y points, you want to find the coefficients a0, a1, and a2, so on, such that it best fits a polynomial equation of this kind, as you've already seen. So how you do this, you use a command called polyfit. All right, so you have polyfit, and then there are 3 parameters that go in. X and y are pretty much your data points, which have to be the same size. And then n determines the type of equation that you want. So if you want a line, you specify n is equal to 1. If you want a parabola or a quadratic, you specify n is equal to 2. And then 3 for cubic, and so on and so forth. Okay, and then the output will give you the coefficients in descending order starting from the highest power that you specify. So if you wanted a cubic, this would be a3, a2, a1, and a0. If you wanted a parabolic, this would be a2, a1, and a0, so on and so forth. Okay, so it will figure out the best coefficients to derive a polynomial equation that will draw that'll match most of those points as best as possible. So A has the coefficients in decreasing order, just like what we've seen in in the TF command. So let's do a quick example. Let's say we have the following data. For example, you have x is equal to 10, 15, 20, 25, so on and so forth, and then we have y is equal to this stuff. Okay, so let's try fitting a straight line and a quadratic line through this data by regression. So what we're going to do is we're going to figure out what the coefficients are. All right, and in this case, what we're going to do is we're going to find the equation of the line for A, and we're going to find the equation of the parabola for B based on these points. So this is linear and this is quadratic. So now let's plot the points on the graph. So what we're going to do is we're going to show what the original data points look like, and then we're going to show what the line looked like and what the parabola looks like after you perform regression. So if you take a look, what I'm going to do is I'm going to specify points from 10 to 75 because the range of x values is from 10 to 75, so that's 0.1. And then what I'm going to do is I'm going to find what the points are along the line. So what you're doing is you're going to use the coefficients that you derived from the regression, and then what you're going to do is you're going to take each of these points and put it through this equation so you can actually plot what the line looks like for the regression. And then you can do the same thing for the parabola when you decide to do this. So what you're doing here is you're trying to draw what the line of best fit is for both the parabola and the quadratic, parabola and the line. And then what we're going to do here is we're going to draw the data points by themselves, right? So x, y, and then blue, they're circles, and then we're going to draw the line, the equation of the linear regression, which is in green, and then we're going to draw the parabola, which is in red. We're going to label the x and y axis. We're going to give it a nice title, linear versus quadratic regression, and then the legend. The first set of points deal with your data points. The next set of points is your line, and then the next set of points is your parabola. And this is what you get, right? So the difference between the line and the parabola is not too much. It's not too different. The regression totally depends on the points that you have. So it's going to be very hard to draw a line of best fit through all these points because the points are so sparse or they're so separated. So the best thing that you have to do is you just have to take a look at what the line looks like and then figure out which order you want. So you can keep increasing it. Try 3, 4, or 5 or so, and then see what you get, and then hopefully it'll give you something that will give you an equation that'll match those points the best. Okay, so what we're going to do is, this is the third last topic we're going to cover. So what's going to happen is, let's say we wanted to calculate the integral, or the area under a curve for a set of x and y points, and we don't know the actual function itself. So what we're going to do is we're going to estimate what the area is using numerical methods. So what you're going to do here is you're going to calculate the area under the set of x and y points using what's called the trapezoidal rule. So you have a set of x and y points and you want to calculate the area underneath the curve. And how you do that is between each pair of neighboring points you form a trapezoid and you calculate the area that best fits under this trapezoid. And then what you're doing is if you want to find the total area under the curve, you just add up all the trapezoids together and that's what you get. And then you get the total area under the curve that way. Because how do you do this? You use what's called the trap-z routine, or the trapezoidal rule. So how do you call this? All you do is you specify a pair of x and y points, and then so this is the x and y data that is unknown, that's known to you, but you don't know the function is. You run the trap-z command, and then it gives you the area that is estimated underneath the curve using trapezoids. So just a quick note of caution. This is the estimated area. If you form trapezoids around pairs of points, it'll inevitably lead to what's called overestimation and underestimation. Because what's going to happen is that you might draw the trapezoid, which will calculate the area outside the boundaries of the graph. So it'll actually add more area, or it won't estimate as much area as you want. So just take this with a grain of salt whenever you calculate the area. But at least this will give you an idea of what the area is. So last but not least, we're going to go through numerical solutions to differential equations, and then we're going to go through sorting arrays, and then we're going to finish. So this is the last advanced topic before we move on. How to calculate numerical solutions to differential equations. So most computer scientists and mathematicians, they rely on calculating differential equations numerically, mainly because solving differential equations analytically for a lot of the stuff that we grab on in practice is infeasible. So the output, the different. So usually, when you're dealing with a differential equation on paper, you usually get a function that is with respect to some variable, time, x, y, or whatever. But when you're doing a differential equation, when you're solving it in terms of numerical methods, you don't get a function anymore. What you get is an output that is an array of points. So each point in the array corresponds to what the actual solution, or what the data point, or what the y value is for a particular point in time. So there are many different methods to solve differential equations numerically, but I'm going to show you things that rely on matrix algebra, because MATLAB likes matrices. So I'm going to show you what is the easiest that I can think of that can relate to this kind of stuff. So here are the steps. So we have a differential equations. Represent each derivative in terms of their numerical estimates. So if you've taken numerical analysis or any other course where you want to calculate the derivative numerically, there is an equation that you can use to estimate what the derivative is between pairs of points. So if we're going to let t sub k represent the time at index k, and we're going to let yt be the actual function or the constraint that we know of. So therefore, for just succinctness, what I'm going to do is I'm going to let y sub k be what the y value is for time k. Alright, so it's just going to be y sub k. So from literature, the numerical estimates for the first and second derivatives are the following. So this would be what the first derivative is. You have the yk plus 1, so you're looking ahead, and then you're looking behind. So so when you're at a particular point, you find the point ahead, you subtract it with the point from the beginning, and then you divide by 2h. H is what's called the step size. It's the increment between successive time points, and we're going to assume that they're uniformly spaced here. And then this is what the second derivative is. So you're going to use the current point, and then 1 point ahead, 1 point behind, and then you're going to weight the current point by 2, and then you're going to divide by h squared. So this is just in literature that you find these. So to calculate the step size and time points, to calculate the step size, you use b minus a divided by n. So if you remember Riemann sums, this is how it's defined. If you want to calculate the time points, you do a plus I times h. So this is stuff from Riemann sums or whatever. So you want to figure out how many what the time increments are, and that's how this is calculated. And to calculate the time points, you do this. So I is the particular index that we want, right? So what you do next, so you calculate the step size, you calculate the time points, you substitute your numerical estimates. So what you're going to do is represent the, okay, I did that already. And then now what you're going to do is once you figure out how many derivatives you have, you substitute those numerical approximations into your equation, and then what will happen is that you're going to sub in I is equal to 0, 1, 2, 3, all the way up to n, and then you're going to have a system of equations, and then you're going to form this into a matrix equation and solve. So, for example, let's say I have this differential equation, double derivative minus, first derivative is equal to some constraint. We know that the first time value and the last time value are both going to be 0, and we know that the constraint is 125 times t. So let's solve this for time values between 0 and 1, 0 to 1, and let's also assume 100 equally spaced points. So first, what we're going to do is we know what the first and second derivative constraints are, the actual equations. So we're going to substitute those both into here, okay? And then what you're going to do is you're going to collect like terms. So you're going to do common factor, and then when you subtract these, you're going to get this. And then I'm going to bring 2h squared over here. So this is what we call a difference equation. And then what you're going to do is you're going to substitute values from I is equal to 0, 1, all the way up to n. And then you're going to get a system of equations. You represent it in terms of a matrix, and then you solve. So I know that for the beginning, when t is equal to 0, it's just 0. When t is equal to 1, or the very last time point, I know it's 0 as well. So those are the constraints that we have. So finally, what's going to happen is we substitute I is equal to 1, right? You get this equation, right? So when you substitute I is equal to 2, you get this. So remember this equation here, when you substitute I is equal to 1, I is equal to 1, this becomes y0. This goes away because y0 is 0, and then you just get this part. And then you keep substituting values in, as so. When you get down to the n minus 1 point, because we know what the end point is, that's 0. When you, let's see here, this is a mistake. This should actually be n. So what's going to happen is this becomes 0. Okay, so cancel this out because this is y of n. This becomes 0, so you get this. So what's going to happen is you're going to have n minus 1 equations, and then you write it as so. Right? So you can represent this as a matrix equation. All the blanks are zeros. And then all you have to do is, if you want to solve for this differential equation, all you have to do is just find the inverse. And then so remember, all these function values here, they are represented as such. So to solve for this system of equations, you just take the inverse of x and then times by f. So how do you code this? It's very simple. First, you got to define your constants. So you have 100 points, and then I know the beginning and the end time, and then this is my step size, right? B minus a divided by n. These are the time points that I want. So remember, this is a plus I times h. The reason what I'm doing here is I'm making this a column vector because the f vector is column vector as well. So if I do this, and if I substitute this into my function, it's going to be a column vector already. So this will figure out our time points, a plus I times h. And we're going to define our function handler. This is just 125 times t. And then what we're going to do is we're going to figure out what the right-hand side is. You're going to have 2 times h squared times the function, which is on the right-hand side here. Okay, so you're going to have all these values. And then now what we're going to do is we're going to create the left-hand side matrix. So what's going to happen is you're going to create a matrix of zeros, right? Because all this stuff is going to be 0. And then what we'll do is we'll modify what we need so that these entries are non-zero. So create the first and last row. So the very first row, the first element is minus 4. And then the second column is 2 minus h. And then the very last stuff is 2 plus h and then minus 4. So that's what we're doing right here. So we're creating these and we're creating these. Because n is the very last matrix, right? And then what you're going to do is you're going to create the rest of the rows. So what we're going to do is this is a for loop, right? So you're going to go from I is equal to 2 to n minus 1. What will happen here is that for the second row, you're going to go between elements 1 and 3. So if you take a look, if this is my second row, so for the second row, right, I'm going to go between elements 1 and 3 and put that in. For the third row, I'm going to go between elements 2 and 4, keep going all the way to the end. And this is what I get. So for the second row, and then this will be 1 and 3, you'll put this in that particular row. And then when I is equal to 3, we're going to go from 2 to 4, and then you do that. So what you're doing is you're actually populating this in a tri-diagonal fashion, just like what we did. And then what we're going to do is we're going to find the inverse of the system, right? So these will be our y points. And then what we're going to do is we're going to plot the numerical solution of the differential equation, and this is what we get. So you do plot, and then the time is on the, this is in seconds, the x label, and the y label, you have amplitude, and then you have the solution to the differential equation. That's your title of the graph. And that's what it looks like. So this would be what the numerical solution to the differential equation is. So if you were to solve it analytically, and if you were to find that equation with respect to x or time, or if you were to plot this, you'd get something like this. Okay, so last but not least, we're going to take a look at sorting. So if you have an array, and you want to sort it in ascending or descending order, you use what's called the sort command. So you do sort, and then bracket, and then the array that you want to sort, and then you specify whether or not you want to sort it in ascending order, or you want to sort it in descending order. Okay? You also have the option of not only sorting the array, but telling you where the elements have moved, which index is moved so that it corresponds to the sorted order. So the first two sort the array in ascending order or descending order, and then they place it back into Y. So the next two not only give you what the sorted array looks like, but it gives you the indices of where the original values came from each corresponding position. So for example, if I had this array, 1, 5, 7, 2, and 4, okay, what will happen is if I were to do sort, and then I sort this, and then I want to sort it in ascending order, it just makes this in following order. So 1, 2, 4, 5, and 7, makes it ascending. If I want to make it descending, you do the same thing, right? You just do A and then descend, it'll sort in descending order. And now this one's the really cool one. If you want to sort it in ascending order, and then you have this instance, not only will you be able to sort it, what will happen is that it will tell you which index from the original array corresponds to this new position. So what's going to happen here is that you'll have 1, and then the number 2 moved over here and came from location 4. And then the number 4 came from location 5, so that goes there. And then the number 5 came from location 2, and then 7. So what this does is that it tells you the location where it came from the original array, so that you're able to, it will give you the actual index of where it came from. And then you can do the same thing for descend, right? So what will happen is that this location 7, it came from location 3 of the original. That's where it goes. And then you have the number 5, it came from location 2. The number 4 came from location 5, and then so on and so forth. All right? And that's it. So in this tutorial, I've tried to show you some advanced concepts that you might use later on in your courses or for your thesis. This is obviously not an exhaustive tutorial. Obviously, if you want to learn more, check the MathWorks forums or check Google. They're both your very good friends when you do MATLAB coding. You're more than welcome to contact me for MATLAB help. If I have the time, I'll try to help you. And last but not least, thank you for listening to this video. I hope it was very informative for you, so you can see how MATLAB is very powerful for some of the stuff that you want to do in your courses.